Hi, my name is Wen J, the founder of 3J Tech and a geophysicist with a doctor degree from Colorado School of Mines. Today, I present our development results for a central loop transient electromagnetic exploration system. The system uses an extended linear ramp time so that a smaller loop size could be used. The contents of the presentation are: first, I will present an extended linear ramp current waveform. Second, I will discuss the effects of ramp time. Third, I will show the modeling results and resolution analysis. Fourth, I will provide two field examples. Lastly, I will propose an ELR TEM deep sounding exploration in Singapore with the government authority. Figure illustrates the current waveform of the loop transmitter with an extended linear ramp time. The example configuration consists of a loop measuring 2.5 meters by 2.5 meters, with 8 turns. The current amplitude reaches approximately 28 amperes. The ramp up time is 2010 microseconds, while the ramp down time is 960 microseconds. The current waveform is bipolar, indicating that it includes both positive and negative pulses. To investigate the dynamic range for the receiving system with different ramp times, an Earth model with a thin conductive layer at 60 meters in a 30 ohm meter half space was used. The transmitter and current waveform are shown on the previous slide. The curves display modeling results of the transient electromagnetic with various ramp times. The dynamic range required for 1000 microseconds is approximately 60 dB, while the dynamic range needed for 10 microseconds is around 150 dB. The figure presents ELR TEM modeling results with a 1000 US ramp time for the Earth model on the right. It simulates the detection of a conductive layer at 10 ohm meters in a resistive host rock, such as shallow groundwater or mining exploration. The curves in different colors represent varying depths to the conductive layer. This slide shows the resolution analysis for the previous model. ELR TEM has a steady current of 30 amperes. The loop measures 2.5 meters by 2.5 meters with 8 turns, and the receiver is a 1.2 meters by 1.2 meters air loop with 100 turns. The analog to digital converter is positive and minus 2.5 volts bipolar. Numerical modeling shows the peak signal at approximately 6.0 times 10 to the power of -8 and the minimum resolvable signal at about 1.0 times 10 to the power of -12. The TXTR moment is 34,560 with amplification around 1,206, resulting in a peak signal of about 2.5 volts. The minimum resolved signal is 4.17 times 10 to the power of -5. Significantly higher than a 24-bit analog to digital converter at 2.98 times 10 to the power of -7. The modeling results with a 1000 microsecond ramp time for the Earth model on the right are shown. The curves represent transient electromagnetic responses for first layer thicknesses from 5 to 150 meters, simulating conductive layer detection in sediments, useful for groundwater exploration and mining. The results show distinct curves for different models. This slide shows the resolution analysis for the previous model. The minimum resolved signal of 2.5 times 10 to the power of -5 volts is about 2 orders higher than a 24-bit ADC. Modeling indicates an investigation depth of approximately 150 meters, where transient curves from the target layer are distinguishable. This modeling involves a conductive layer with a resistivity of 10 ohm meters. Buried 3000 meters deep in a half space with a resistivity of 200 ohm meters. The transmitter measures 40 by 40 meters with 3 turns. The falling ramp time is extended. A discrepancy between the two curves is observed. The receiver loop moment is approximately 45,000 square meters, and the gain is around 80,000. The minimum voltage that needs to be resolved is approximately 1.5 times 10 to the power of -5 volts, which is about 2 orders of magnitude larger than the resolution of a 24-bit ADC. This modeling is for a conductive layer of 0.3 ohm meters buried under 3000 meters deep of a 60 ohm meters half space. The transmitter is 40 by 40 meters by 3 turns. The falling ramp time is very long. We could still see the discrepancy of the two curves. However, the receiver loop moment is about 45,000 square meters, which the gain is about 17,000. The minimum voltage that needs to be resolved is approximately 2.9 times 10 to the power of -5 volts, which is about 2 orders of magnitude larger than the resolution of a 24-bit ADC. The initial case takes place at a construction site with shallow core drillings. The figure shows the topography of the area, including the survey sites. The survey area is located around a valley, surrounded by high hills on 3 sides. XD indicates the ELR_TEM sounding stations, while BH represents the core drilling locations. The figure illustrates the locations of the coring wells and ELR_TEM sounding points on the left-hand side. On the right-hand side, examples of the coring results are presented, indicating depths to the water level, the gravel formation, and the sandstone formation. The findings demonstrate that ELR_TEM can extract deeper information, with patterns that correspond to the interpretations derived from shallow core drillings. The contour maps on the left of the figure show that the sandstone formation depths are deeper near BH3 and rise gently to the left. The right-hand side shows transient curves from ELR_TEM, indicating lower late-time resistivity near BH3 that rises again to the left. This pattern matches the core drilling results. The second survey targets an area with a shallow low-resistive zone identified by our magnetotelluric array survey. Results show that the ELR_TEM low-resistivity zone matches the magnetotelluric survey, refining its definition. Soundings are grouped into 5 categories based on late-time slopes, with the first group having the highest conductance. Points near the anomaly area exhibit higher conductance, and ELR_TEM surveys further delineate this shallow conductive zone. Advantages of ELR_TEM is itemized as followed. First, the transmitter loop size for ELR_TEM is approximately 20 times smaller than that of a traditional central loop. Second, the traditional central loop TEM investigates depths to about 3 to 5 times the transmitter diameter. Numerical modeling shows central loop ELR_TEM can reach depth 60 to 150 times the transmitter diameter. This system is effective for exploration in urban and rough terrains, such as Singapore, where open sites for traditional transmitter loops are scarce. Third, the reduced separation among central loop ELR_TEM due to small loop size improves horizontal resolution. Fourth, another benefit of the system is its ability to interpret data. Using 1D inversion at each station will enable the creation of a 3D structure. Fifth, increase signal-to-noise ratio by stacking more, like other controlled source surveys. Central loop ELR_TEM could have shorter station spacing, enhancing horizontal resolution. This figure shows it can have 9 stations compared to only 1 in a traditional TEM transmitter loop. The final task in the project scope is to perform a deep-sounding survey in Singapore with authorities. Google Earth shows potential sites for the central loop ELR_TEM survey with loops larger than 30 meters by 30 meters. Results will be compared with existing data and published with official permission. Thank you for your attention. We believe the ELR_TEM will be valuable for exploring urban areas like Singapore, identifying sites for geothermal system development and carbon storage, and conducting civil engineering surveys.